Okay, welcome to Algorithms Live. This week we have an interesting episode for you all. It features this idea of solution bags, a little bit of a weird way of thinking about data structure problems and special kind of data structure problems. So instead of focusing on what a data structure should be doing or teaching you a specific data structure technique, it's really just a way of thinking about problems involving data structures. And also you can think of it as like an alternative to dynamic programming or even certain types of brute force. And so I've found this handy if I want to do, there'll be problems that are backtracking kind of problems, and you can modify this to be a special type of brute force. And it just makes it easier to come up with clever solutions, in my opinion. So it's really just a way of thinking about data structures. It's a little bit different. I haven't really seen anyone talk about data structures in this way. So the reason I'm doing this episode first is this is also how I think about convex hull optimization. I view it from this lens of solution bags. And a lot of times I'll be analyzing a problem using this technique, and then a branch off that analysis is convex hull optimization. It's not, I look at a problem and know that that's going to be relevant. I start with this kind of analysis first, and then if it makes sense to do convex hull optimization, I do it that way. And so I've solved a large number of problems with this technique, and it's led to more creative solutions in my own thinking. There's been cases where there'll be code forces problems involving interval tree or segment tree, and I end up solving it with other data structures. And so I wanted to get this out there first before we cover convex hull optimization in future weeks, and just teach this technique about thinking about problems. So we're going to start off with the brute force version of this technique. And we're just going to solve a really common, well-known problem called subset sum. And our version of subset sum could have really big numbers. So we're going to have up to n integers, up to 18 integers. But the numbers themselves could be quite large. So you may be thinking the easiest way to do this would be using a DFS and do a kind of try all possible subsets. That's one way. You could loop over all binary strings as well. And just try all subsets that make sense in terms of this problem. But what I'm going to do is I'm going to take a step back. So we're starting with this simple example because there are other variants that we can use to attack this problem. And even though there are other simpler ways to code the solution, I want to just change your way of thinking about this problem through the lens of solution bags. So here's the idea with a solution bag. First, you start off with a bag. And so if you don't know, bag is the simplest data structure you can have. It's even simpler than stacks or queues or anything like that. All you can do with a bag is put things in and take things out. And that's it. It makes no guarantees about the order things come in. Like if you know for stacks, it's first in, first out is queues, or last in, first out is stacks. It makes no such guarantee. And the reason bags are really great for analysis is they're so simple, it allows us to convert it to any other data structure fairly easily because there's no restrictions on this data structure. There's no way it's organized. There's no way things are coming in or leaving. So there's a lot of flexibility here in terms of this very simple data structure for what it actually could be later. So if you're working a problem and then eventually you need your bag to do something a little more complicated, you can just replace the bag with that more complicated data structure, and now you have that more power. So for the subset problem, what we're going to do is we're going to save what's called a partial solution. So initially, it's just an empty set. I haven't decided to take any new elements. And then for subset sum, I might have some numbers that I want to actually store. So when I come across a new number, like, so let's say this 2, what I can do is I can update the whole bag. There are two options. Either I look at everything that's currently in the subset, leave it in the bag, but this new element I consider adding to every single partial solution, every single partial subset that I've constructed. So I'll construct a new subset here, and that gets added to my bag as well. Then I come across the 18. I could add it to this empty set, or I could add it to the 2. And so this bag is going to start growing exponentially. And I'll keep doing this as I go. And eventually I'll get all possible options. So I'm not going to draw them all out. Maybe I'll just do -5. So -5 could be added to the empty set, to the set containing 2. I could have everything. Or I could have add it to 18, and so on. Now, you could also do this with DFS. You could also run a DFS and consider for every single element, take it or not take it. So you can look at the solution bag technique is almost like the breadth first search counterpart to backtracking. That's one way you can view this technique and see, can I take things or not take things, and try all possible options. So you could run through all possible subsets of values and put them into this bag. And then when you eventually reach the end, you'll have all your full solutions to evaluate. An advantage here is you can actually prune on partial solutions. So if you get out to a certain point on all these partial solutions, and you can basically preclude answers, then you can eliminate them from your bag. So let's say for some reason we know we don't have to have this number, and you can do certain types of pruning. So sometimes it's easier to do your pruning depth first search style, but sometimes it's easier to do your pruning breadth first search style. So in the case of brute force, you can use solution bags in this way. But this is honestly not the most powerful use case for them, but I thought it would be a good starting place. So the goal here is to keep track of partial solutions, and specifically all partial solutions. Another name I've heard thrown around for solution bags as a special case of them, you may have heard, is stack of incomplete subproblems. And so the idea is to keep your partial solutions around, but specifically this technique is keeping them as a stack instead of a bag. So you can view solution bags as a more general stack of incomplete subproblems, if you've seen that technique before. All right, so let's get on to a new problem that will be a little bit more interesting in terms of solution bags, and we'll slowly get better solutions. So our first case here is we could end up having some number of numbers in a row. And I talked about this problem a little bit in the blog. And what we want to do is we're given some target number, let's say 8, and maybe 17. We'll take 17. So some target number t, and we have to find the contiguous subarray, the smallest contiguous subarray that sums to greater than that target value. And I believe that's this right here, just this 8 and this 12. So if all the integers were positive values, then this problem would be pretty easy. We could use another technique to solve it. So here's the idea for that solution. We could start at some number. And then you could very easily, if you brute force your starting position I, you could binary search for how far out to go, and then do something with prefix sums to figure out exactly how far that should go. So that gives you an n log n solution. If you're familiar with the two-pointer method, one thing you could do here is you could keep track of I and move some j pointer to the right. And then as you've found the optimal j for this range, so this is a sum greater than 17, I could move the second pointer to the right and keep doing this two-pointer method to end up getting my answer so far. So that's also 17. So I end up with both my pointers here. I try moving my pointer to the right. That's less than 17, so 12 plus 4. I move this to the right again. I get out to here. So for every single starting location, I could find what the minimum length is. And that would get my runtime down to order n, because it's just a two-pointer method. The problem starts to be when you throw in negative values. So it's fairly easy to break the two-pointer method. And here's a case that breaks it. If you're allowing negative values, that is. So if I'm doing two pointers, I start here. I run my sum up to this point. At this point, I'm at negative 16. So then I keep moving to the right, hoping to increase my sum. I move there, I get to negative 4. Then my pointer moves a little bit further, and I get to 4. Keep moving, it ends up negative 4, and then negative 8. It's fairly easy to make cases that just this two-pointer algorithm just no longer works. It can't tell us anything smart about what's the minimum subarray. But this minimum subarray starting from right here could be as small as possible. So we've deceived our algorithm. Then you could start thinking, well, we only want to start at positive values. So I could try something with that and maybe do a binary search. And it's not binary searchable because it's no longer strictly increasing. So that's a problem. And so we just start running into a bunch of problems as soon as we start allowing negative values into this problem. So this is where solution bags will come in. So there's a fairly obvious n squared here. I could just try all possible I and j and keep a running sum and get my answer. So I'm going to first come up with an n squared solution bag solution to this problem. And then we're going to be a bit clever with what we replace the bag with to solve this with a data structure. So this is where you start seeing solution bag technique show its advantages. So here's the idea. What I'm going to do is I'm going to pick an ending location. I'm going to brute force the ending location of my sequence for a solution bag. And my partial solutions are going to be every single subarray up to and including that position. That's how I'm going to characterize my partial solutions. So let's start on the left. I'm going to start here on this number. What's my partial solution look like? Well, I'm going to characterize it with where it started. So let me write the indices. Well, that's readable anyway. So it starts at index 0. So I'll keep it as an ordered pair. I comma the sum that it has. Okay, so I'll make my bag a little bit bigger. It's going to get full pretty quick. So I get 0. And then my sum currently is 2. Okay, so I move on to this next location. Negative 8 is my next number. So my options are I can start a new running sum, or I can increment all my running sums by negative 8. So I do that. I increment this by negative 8. I get negative 6. My starting location could be 1, and my sum is negative 8. I want to point out a secondary thing. At any given time, I want to know what's the shortest sequence ending at this location that sums to greater than my t value, in this case 17. So I can do that fairly easily. I just loop over the whole bag, and I find the only thing that sums to greater than 17, but ends up having my solution. So let's move to the right again. I can start a new one. I basically increment everything by -8. So this ends up going -14, -16. And then I also consider adding -8 to this data structure. So I start from 2 and have -8. And I can keep going like this. So it's saving all my partial solutions in the bag. And so this is an n² solution. And you can think the brute force solution is also n². So this isn't anything special right now. But conceptually speaking, this is what's going on. I'm starting at maybe position I, and I have all these running sums. And this is what's getting stored in my bag. I have all these intervals up to and including that position. And so when I come across a new element over here, what I do is I extend each of these. So maybe I'll use a different color. I extend each of these to contain the new element in my bag. And then I add a new element to the bag. And that's the idea with the solution bag. So this one ends up being a lot better than the subsets example. I know my bag is going to grow to be at most O of n in size. And then my queries right now on the bag, finding what that minimum element is also O of n. So I end up with an n² algorithm for finding this consecutive sum. But I can do a bit better here. So this is where I start analyzing the data structure. So right now it's just a bag. It's got all these partial solutions. Let's talk about what's going on here. If I look at my data structure, I start to notice some properties that emerge inherently in my data structure. If I have something with a 1 here, and I have something closer to my ending location with this 2 that has a smaller value, notice as it gets extended, it's going to change by the same amount. In other words, I can immediately know that this gets deleted. So in other words, if my I value, so I'll just look at the I values. So if I have 2 positions, I and j, so it's I and then some value of I, and then j and then some value at j. If I is less than j, then in order to even consider it being around, what I could do is maintain that v of I has to be strictly greater than v of j. If this is not true, then this I isn't worth keeping around. It should be fairly obvious to see because I have a shorter subarray that meets the criteria. So what this is, what I've written here is what's known as an invariant that I'd like to maintain on my data structure. I would like for every single pair of elements in my data structure to maintain this property. So I'd like to maintain that if it ends up having an earlier starting location, then it has to have a larger running sum right now. That's the invariant I'm choosing to have on my data structure. So what invariant means is it means not to change. So I'm going to keep this property on my data structure for the lifetime of my data structure. So this is one invariant I'd like to maintain. Okay, so this is where I start thinking about how do I want to organize my data structure? Because right now it's a bag. It doesn't have any organization. And I want this property of I being less than j to maintain that the sum up to that point is greater than the sum up to and including the other point. Well, this is where I change my data structure out for a stack. So now instead of being a solution bag, it's a solution stack. And it's storing all the partial solutions up to that point. And when I'm coming across new solutions as I go, then I want to maintain that invariant. An added bonus to this invariant is I now know that as I go up the stack, the values are going to go down in size. So it's basically, this is a sorting criteria. My stack has two properties. It's increasing as it's going up in size. So let's run through this example again, but using a stack. Erase some of this. Let's replace some of this. Keep some of this around. Okay, so I've just changed it out for a stack. So now I have a stack. So I push on 0, 2. And then I come across 0, 1. So I go 1, comma, -8. So it's starting its new run. But I also have to consider changing this value. And I know that 1, -8 is strictly less than that other case, in which case my invariant is maintained. I is less than j does imply that v of I is greater than v of j. So I do the same thing again, end up placing 2 on my stack with -8. So it ends up being -16. Or yeah, -8. This becomes -16. This becomes -14. And now I have my first problem. This -1, -6 does not meet the stack invariant of what I ended up adding. So when I'm pushing something onto the stack, what I can guarantee up to that point is the entire stack meets this invariant. Luckily, this invariant is transitive. So if you ever have the property A is greater than B and B is greater than C, then we also know that A is greater than C. So if I maintain it, if it's already sorted, and if I just maintain adding this new element to the stack from top down, and I keep removing elements from the top of the stack until it finds its place where it maintains this invariant, I basically can guarantee that the entire data structure maintains this invariant when I leave the stack, which is good news for us because we want to keep that property persisting throughout the lifetime of the data structure. So I don't have to like loop through the whole data structure, all pairs, and make sure that this property holds. I only have to maintain it for the top of the stack. So when I'm trying to add my 2, -8, basically remove the topmost element, and now my data structure, which is my solution bag, I've pruned out a case, a partial solution, and put on a new case like this. I can go again. This becomes -10. This becomes -16. And then I plug on 3, -2. Oh, yeah, I guess I should have taken off more than just that. Yeah, because this would even get popped off my stack as well. Oops. So 2, -10, and then I get out to this -2, and so I get 3, -2. This goes away from my stack. And I keep doing this as I go. So starting from 3, I could get -2, and then I pop or push 4, 12 onto my stack. And so this would also wipe this out because that so when I come across this element, I increment this by 12, I end up getting 20. And then I'll push this next one onto the stack is 5, 8. So I'm keeping all my solutions around, but I'm only keeping the relevant ones around. So, so far, adding things to stack, removing things from a stack, they're pretty fast in the amortized sense. I can, for each partial solution, I'm pushing it onto the stack at most once, and I'm removing it from the stack at most once. So over the entire course of the problem, it's going to be order n work. The only thing that's expensive about my data structure right now is I have to go through every element of the data structure one by one and increment this value here. So that's pretty slow. But otherwise, I'm doing pretty good with the data structure. So I'm starting to think of what I need. Well, if you want to increment an entire data structure by some value, instead of looping through it, what I can do is I can keep an auxiliary value on the outside, and then instead increment this value. So let's say I want to add 2 to everything in this data structure currently. I can add 2 to my auxiliary variable. And now when I pull something out of the data structure, I just add my auxiliary variable to it. So I'll know that 8 plus 2 equals 10, or 20 plus 2 equals 22. So this is a technique called deltaing. And so the idea is you store some auxiliary extra information outside the data structure that's going to maintain how much that changed by. Instead of looping through every value in the data structure and increasing its value, what you can do is you can keep this auxiliary variable, increment this value instead. And now when you put something in the data structure, you have to subtract out this auxiliary variable before it comes in. So if I put in the value 8, I actually put it in the data structure, it'll become 6. That way, when I take it back out of the data structure, it'll be 8 again. But this auxiliary variable might change in the lifetime it's in the data structure, so that value will change too. So it's a very common technique. So our increment, so if we write out our properties that we needed to maintain the invariant. And that was the I less than j implies vi is greater than vj. And the second property was increment everything, which we can get away with by doing this delta technique. Maintain an auxiliary variable and just go. So it very naturally led us to a stack because this data structure, or this property was very easy to maintain as a stack. And it also very easily led us to this property of deltaing because we need to increment everything, not just some subarray or not just something specific. So we're off to a good start. Okay, so now we have a problem, and that is we're maintaining our solution bag. We've got fast increment and query. What we need to do is we need to figure out what's the smallest value of I in our I pair, I-VI pair. What's the smallest value of I, our largest value of I, because it'll make the interval as small as possible. What's the largest value of I that has a VI greater than our target T? Remember, we had this target T value we're given. We have to figure it out. Well, if we look at our data structure, if we keep adding things, it'll start to look like this. Right? And you'll notice as we go up to the stack, its VI values are going to be decreasing in value. And that's all thanks to the invariant that we imposed on our data structure. So if we don't use a real stack, if we use an array, what we could do is we could binary search this data structure, looking for the thing that's highest up in our data structure that's greater than our T value. So if our T value was, let's say, 6, then I would want to binary search and find this location in the array. I would know that at that ending location, 5 ends up being the furthest right value that is greater than or equal to my T of 6. So I can just binary search this data structure, find that information. And that's an added perk of maintaining the invariant we chose. This data structure is now binary searchable. So pretty cool. So putting those things together for this problem, we end up with an n log n solution. It's pretty good. We can actually do better. We can bring this down to order n. So let's figure out how that works. All right, so this is the last observation we're going to make. So suppose we have a solution so far that covers some range. And we happen to know that this binary search value was the time where it covered this range. We can make another observation. We're not going to find a better interval by extending this range at all. In other words, this is the most optimal answer we can have at any given time. So we can just delete it if that was the best answer we found at any given time. So in other words, we don't have to do a binary search for that value. What we could do is we could change this stack. So right now, what we currently have is a stack to a data structure called DEQ, which stands for double-ended queue, or you could call it DQ. And the idea here is if I'm looking for that first value greater than t, what I could do is I could keep removing values from my stack until I end up hitting a place where it doesn't meet that criteria. And these ended up being candidate solutions that were good enough to be greater than my t right at that moment. So things are getting removed once from this double-ended queue. And putting all that together, I end up with a nice O of n solution to this problem. Pretty cool. So putting it all together, the idea is we've taken this analysis technique of solution bag. We've analyzed the problem, like criteria that we want to impose on the bag for pruning purposes. We don't have to keep all partial solutions around. And as we did the analysis, eventually we got down to this data structure that is just a double-ended queue that basically has this extra stack invariant imposed on it, extra data structure invariant imposed on it, and can solve our problem. So that's the basic idea behind solution bags. So let's move on to another problem using this technique that can come up. So we have this problem called, it's this USACO problem. You can look at it on the blog post for this episode. It's called generic cow protests. So this is from USACO, and it was from February 2011. And Neil Wu wrote this problem, so give him credit. Here's the idea. You're given a sequence. Okay. And what I'd like to do is I'd like to partition this sequence into subsequences. But the partition needs to be positive in sum. So I could take the whole thing, and notice this thing sums to 3. So 2 plus 3 plus negative 3 plus 1 is 3. Another way I could partition it is 2, 3, negative 3. Actually, I'll do it right on the thing. This is another partitioning. So I end up having one that ends up having sum of 2 and sum of 1. Another partitioning that could exist is 2 and then everything after it. And that sums, those are both positive. Well, I guess it's non-negative because they also say that this could occur. You could have 2, 3, negative 3, 1. So let's take a moment to look at the bounds. The bounds are up to 10 to the 5th. And the values themselves are from 10 to the 9th to negative 10 to the 9th. It could be pretty big. Okay. So let's start analyzing this in terms of solution bags. So we have our number here, our sequence. What I'm going to do is I'm going to keep track of state, a lot like I would be keeping track of dynamic programming. But instead of having a table keep track of my partial solutions, I'm going to just keep them in a bag. So I'm not even committing to having a DP table here. I could have any data structure I want for the partial solutions. So what I'll do is I'll keep track of what my running sum was up to and including that value. So it's going to be sum up to that value. and the number of ways I could get to that state. Those are the two pieces of information I'm going to store. So here's how this works. Initially, I have a sum of 0 and only one way of getting to there. So a lot like dynamic programming, you're going to characterize your state and what your answer is all in one, except instead of storing it in a table, a nice form like that, we're storing it in this vague data structure that doesn't really matter. That's the change here when we're thinking about solution bags. So now I come across this 2. What are my options for modifying the bag? Well, I could extend my solution to use 2 up to and including that point. So I can extend everything that's in the bag to increase by 2. Or I could cut right at that moment and start a new running sum potentially. So for this very first piece, I don't actually change anything. I just increase this by 2. And I only have one option here. So I get to the next 3. My options are I either take a cut from everything in my solution bag. So all my partial solutions are up to that point. I can only put a right parentheses between the 2 and the 3 if the value is non-negative. So if it's 0 or greater, then I can put a cut here. So I could start a new running sum right at 3, and there'd be one way to do that. That's putting the cut. Or I could increment this running sum of 3 and then get to 5. All right. So moving on, I get to -3. So I end up modifying everything in my bag by -3. OK, so actually, let's talk about the change. I can look at everything in the bag. If anything is positive, then I could end it right there. There are 2 values that are positive. So starting right at -3, I could have 2 ways of being at -3, ending both of these intervals here, right at that moment, putting my right parenthesis. And there are 2 ways to do that. So I just sum the right values. And then I have to consider extending these right values by 1. They extend, they're a little bit further. So this becomes 0, this becomes 2. And so I plug in my new -3, 2. So this is the sum up to and including that point of my answer. And so then I get to this last value. Well, this is now negative, so I can't consider that one to increment. But these are both non-negative. So what I can do is I can take those 2 sums. So I end up getting 2. There are 2 ways to sum greater than 0. So to end right here with a right parenthesis. It's saying that I can't end like this. So that's why this one's excluded completely. So there are 2 ways to end right there and then start my running sum of 1. So that's going to get added to my bag. But I also have to consider incrementing my entire data structure by 1. OK, and then add my new 1. And if you remember before I did this problem, I said that there were 5 possible solutions here, right? Let's take a look. No, there are 4. And so you'll see they're all right here in my data structure. So my data structure has the case where I took everything. There was one way of doing that. There's the case where I started at 3 and then had some number of ways of doing the previous. So that's stored right here. And then I have 2 ways where my data structure started right at 1 at the end, and then had ways of chopping up what was before it. So you could say my state of my data structure doesn't really care how you parenthesize the things before it at all. That just gets stored in the number of ways to get to that position. And I'm only characterizing the sum up to and including that time. Another thing I could have done is I could have grouped these 2 things together. And that's fairly easy to do. So I could have just grouped the 2 things that sum to 1 to be the same thing in the solution bag. The main change here is I don't have a DP table, so these sums could be anything, so I have to loop over everything. So I end up with a pretty slow solution right now. My bag could get up to order n in size. I have to increment all the values by some amount every time I come across a new value. So I have to increment everything. And I need the sum of all values greater than me. And specifically the sum of the number value that I have here. So I'll call this ways. So the sum of ways of everything whose sum is non-negative. Okay, so those are the two properties I need. So notice I haven't committed to a data structure yet, but I'm just analyzing what properties this data structure needs. And this increment everything we saw in the previous problem. I can just solve this with deltaing. What I can do is I can maintain that auxiliary variable and then just increment it by some value whenever I come across a new value. And so this ends up amortizing the whole thing, or this ends up speeding up the increment everything in my data structure phase to O of 1, which is really beneficial. So that's speeding thing up. So now we just need to know, how do we get the sum of everything greater than me in the data structure? Well, we know a great data structure from doing that from episode 0, and that's a Fenwick tree. So the Fenwick tree should become immediately obvious from the analysis here, that we need sum of all values greater than our current value. But we're not out of the woods yet. So this would work to a degree. We just replace a bag with a Fenwick tree, and then we could get it to work with this deltaing. But we have a problem. Our values are much too big to fit in the table of our Fenwick tree. If you look at this, I have negative 10 to the negative 9, all the way up to 10 to the 9. These values could get really big. And if I'm storing my Fenwick tree, I'd need something like 2 times that, maybe times n, because if everything's 10 to the 9th, everything's going to be incrementing quite a bit at different times. So we need to get around that still. So the values are too big for a Fenwick tree, but I can manage up to a point. At this point, you could use a balanced binary search tree and then do the sum of everything greater than some value in the range. You can do that with a balanced binary search tree fairly easily. So if you wanted to solve it that way, that's a good way of solving this problem. But I'm pretty committed on Fenwick trees here. So I'm going to show you how to get around this. All right, what we're going to do is we're going to analyze this auxiliary variable, how it changes things, because I want to only put things at the insertion point. Well, I'll know what that auxiliary variable is because every time I come across a new value, this is what I change it by. So my auxiliary variable for my data structure is going to be things like 2 or 5 or 2 again. So negative 3 gets applied, or 3. So it's going up and down. And depending on what my auxiliary variable is at currently, that's where I'm going to be dropping things into my Fenwick tree. Pretty cool. So then the only other thing I need to keep track of is where 0 is. Because if I know where 0 is in my data structure at any given moment, then I'll know where to do my prefix sum or my suffix sum using a Fenwick tree. So what we do is we pre-compute all these running sums up to and including that position, and then we coordinate compress on them. So the way you do that is you take all the unique values and you map them to the values 0, 1, 2, and 3 in order. So this coordinate compression is fairly easily done. I did this in the last episode, which was the Steiner tree episode. basically what you do is throw everything into a tree set and then throw them in that order into an array. And if you do erase that binary search, you can always go from an uncompressed value to a compressed value. And if you're in a compressed value, you can just look at the index of that array, and it'll get you out the uncompressed value. Pretty neat. So what you do is you run through the sweep now on these compressed values, and you keep your Fenwick tree on the compressed values. So if I need to increment position 3, I just look at, maybe this was actually a 7. So maybe that's what the prefix sums come out to. So if I change things, if I change this value to be a 5, this will be a 7. Or other way around. You get the idea. Yeah, I already lost myself. Oh well. But you can basically just change this prefix value to be a 7, for example. So if I end up knowing my prefix sum is up to 7, then I just look in position 3 of my Fenwick tree and increment that value. And then I just have to keep track of where 0 is. Well, 0 was at the previous position. So I can do a binary search for 0 based on where I currently am and my data structure, and then do a prefix sum or a suffix sum on my Fenwick tree to end up calculating the sum of everything greater than me, and then add that new value to my data structure. So instead of adding it to a bag, I'm just incrementing a position in my Fenwick tree. So as you can see, solution bag, really the idea is to not commit to a data structure first. So that's our first instincts. What we do is we look at the problem, we analyze what properties the data structure needs to have, then we pick a data structure that meets this criteria, and then use that for our to maintain our partial solutions. Okay, so let's look at this problem. So our third problem tonight, or I guess fourth problem, is let's say we have an almost tree. So what this is, if you look back at episode 1, I talked about this problem. We asked ourselves, could you find the diameter of a tree in order and time? And we found an algorithm to do that, and we proved it worked. And then I asked you guys the question, does that algorithm of 2 DFSs work if you add a single edge to the tree? So originally we had a tree, we add a single edge, it becomes almost tree. And the answer ends up being no. You can't find an diameter of an almost tree using 2 BFSs, finding the furthest point from a random vertex you could pick and then finding a furthest point from there. So I encourage you to work on finding a counterexample to that case. You can basically trick your BFS algorithm to find something that's the furthest away, but it's not an endpoint of the diameter of the tree. And I'll remind you, diameter of an almost tree is defined as the longest of all shortest paths. So you find a pair of 2 nodes. So you want the pair of 2 nodes that are furthest apart given their shortest path. So I think that pair is here and here, just eyeballing it. So we'd like to find what that length is. Okay, so if we root the tree at each of these subtrees, we already have an algorithm around the cycle. We already have an algorithm for pairing 2 of those subtrees together and finding the longest path. That's important because you could be given a tree like this that has really long paths here and a really long path here. So the optimal answer may be found by doing that subtree pairing algorithm for finding diameter that I talked about in the trees lecture. But right now, what we want to do is we want to assume that such diameter doesn't exist because we can find it really easily. And I want to focus on finding diameters that end up going across this cycle some way, one way or the other. So the first step in this algorithm is we're going to compress all these nodes to be the length of path that comes off of them. So the deepest path I could have here is 1, 2, 3, 4. So I'll replace this with a 4. Replace this with a 2. Another 2. So I end up with something like this. And now what I'd like to do is I'd like to pair two sides of the nodes together such that they're far apart from each other. So the cost of pairing two nodes together is the current position and the position on the other side plus the length of the edges between us. Okay. So I'm going to characterize this problem once again as solution bags. What I need is a data structure. So here's my bag. I need to keep track of everything in front of me this time. So what I'm going to do is, no, I'll go behind me still. So I'll keep track of what are all the positions behind me. And I want to keep track of a window. So I don't want this window to get too big because it would have actually been faster to go around the shorter end. So I'll only walk my window out so far. And so let's characterize our partial solutions. Our partial solutions is the start index of where we currently are. Another way you can think of it is the number of edges between us on the cycle. So I'll say edges. And then the cost of going down that subtree, this value. And that's how I'm going to characterize my partial solution, is the number of edges I've taken up to that point and the cost of my partial solution. So if I walk around the cycle like this, I could start here. Well, my answer right now, I've taken 0 edges and my cost is 2 for my partial solution. I walk out 1. Well, now everything increases by number of edges I can use. So I'm considering this window. And what I want to do is I want to put this new data structure in. So it uses 0 edges and it has 0 cost. I go a little bit further, end up getting a 4. So I have to increment everything again. 0 edges used. But now this has a cost of 4. Well, I can, whenever I get to the end of a position like this, what I could do is I could consider pairing it with things behind me. So the pairing would be taking this position here, which is the 4, taking the cost of a partial solution. So the cost of a partial solution is edges plus cost. So if I wanted to pair the longest path down this subtree with the longest path down this subtree, what it would be is 2 plus the number of edges I used intermediately plus this 4. And so that gets me out to that position. So I'll continue on in this way. And I'll get all the way out to this position. And get out a little bit further. And I'll add a 0, 2. And then these all increment by 1. If I put weights on the edges, I would need to increment everything in the data structure by that weight instead. So in the edge weight version of this, it's still possible to be solved. Okay, so we're doing pretty good. So let's analyze the data structure. We need to increment everything in the data structure. That's what we need it to do, to store a range. We need to know the min cost at any time. So notice when two things get put in a bag, you immediately know what the cost is between them because they can only ever be incremented by the auxiliary variable. So that's important to note. And then what we're going to do is instead of recomputing this data structure each time for all starting positions, we need to slide our window around. So in other words, I need to remove the first thing from my data structure, which would be this 2. So get that out of here. And then add something at 0 cost. So these would all be 3s, 2, 1. And then I add my new position in my data structure, 0, 2. So I need to be able to delete the first thing. Oh, and this should be max cost at any time. All right. So the increment everything can be done by our deltaing technique. So that one's pretty easy. I use that technique a lot, and just a lot of our examples today just happen to use that technique, make things a little easier. The max cost at any time. So we need our data structure to determine what's the max in our sequence so far. So I could actually think of this as a running sequence of values, and I'm just interested in knowing what's the max at that time. To make things a little simpler, another thing I could do is just store a single value for everything instead of 2 values. Because once I put it in the data structure, the position doesn't matter. All that matters is the sum of edges used up to and including that point. And then I need to delete the first item. So there's this great data structure called maxq that's really useful here. And the way you implement this is you can actually implement it with a double-ended q plus an invariant. So I'll show you maxq, and then you can see how to implement this problem. Okay, so let's say we have 1, 2, -3, 1, 4, -8, 4. And I want to do sliding windows on this, and I always want to know what's the max value I've come across. So if I start my position here, I'll just put the smallest value on the data structure. If I slide it to the right, notice that I'm never going to add this guy again. So I can only do 2 pointers with this data structure, this maxq data structure. So I'll add 2, but you'll notice that that 2 is always going to be better than this 1 that got added to my maxq. So I can immediately delete this value because it's obsolete. So for our data structure invariant, if I look at ij on the data structure, if I is less than j, if I is lower on the data structure than j, then what we're going to imply is that v of I is greater than v of j. It's that same data structure invariant that we saw on the subarray sum problem. So what I'll do is I'll actually delete this one and always save what the max is. So if I extend my data structure a little bit further, I end up with -3. -3 goes on the data structure just fine. Extend it a little bit further, I get out to 1. That goes on the data structure, actually deletes the -3, comes out to 1. That's better. The reason I don't delete 1, because 2 is beating it, is if I slide my pointers to the right a few times, eventually this 2 may no longer be the maximum, and this 1 has to take over from it. But this 3 will never be the maximum ever again once this 1 is occurring, because this 1 occurs later in the sequence. So let's talk about removal. If we want to remove the first thing from this data structure, I consider looking at the bottom of the data structure and say, hey, am I the max thing possible? Because I'm the first thing in my data structure. I'll know I've been removed if I'm not the first thing, because something else overbeat me. So if I look at the bottommost value and it's not equal to 1, then I don't have to remove anything. But if I slide over here and want to get rid of this 2, well, that's the max. That's the best value currently, so I delete it from my data structure. And so that's the idea with the maxq. You add things to the back, and you maintain this invariant as you're adding things to the back of the queue. And then you look at the front when you want to pull first, and if it ends up being the maximum possible, then you remove it from the front of the queue, and it gets taken away in that manner. What's nice about this max Q data structure is you look at the first element, you always know what the maximum in the range is. It's going to be the first thing in this double-ended queue that you end up having. So it's a pretty nice data structure, and it yields itself well to analysis. Other things, other useful things. Oh, yeah. So let's say we have all 4s. Well, what I want to do is make my data structure not strictly greater, but greater than or equal to. This way, it makes it easier to keep track of the 4s, because if I move this 4 to the right, I'll say, oh, I'm currently the best thing on the queue. What I want to do is I want to delete those. So that way, I delete the appropriate number of 4s if I end up having a bunch of 4s in a row. So it's a small implementation detail. It basically, by keeping the duplicate values, even though these will no longer be optimal because I have this 4 right here that's later and better than my current 4, it'll keep track of how many I need to delete implicitly in the data structure without changing the runtime. So I want something clever like that that makes my life a little easier. So going back to this problem, what I can do is I can replace my bag with a max Q. And then I have the optimal data structure that solves this problem. Okay. So let's talk about this last problem I wanted to talk about. So last year for NAIPC, so NAIPC 16, I wrote this problem called Whiteboard that I posted in the blog about. And I felt like this would be a good one to talk about. So that's what I'm going to do. For this, what I'll do is also switch over to grid mode, because yeah, let's do some of that. It's a little bit easier to explain on a grid how this whiteboard problem works. All right. Okay, so in this problem on whiteboard, you're given some commands that could happen. So you could have something like go up 3, or then go right 7, or go down 2, and go left 4, or go up 3. And then so what this does is a little bit like a drawing program. So you go up 3 on your command, and then you go right 7. So you go 1, 2, 3, 4, 5, 6, 7. We could go down 2. We could go left 4. And then we could go up 3. And you could draw a picture like this. But a side effect of this problem is your marker could dry out after some amount of time. So you're given these commands, and then you're given a picture, and you're told that the marker could have dried out. And so after a certain point, the marker stops being a marker, it starts being an eraser. So you might get an image like this, even though I did that drawing pattern like here. At time 18, the marker could have dried out, and this is what the picture actually looks like. And you have to determine, given this picture and given these drawing commands, what could the picture have possibly, what was the earliest time and the latest time the marker could have possibly dried out? Okay. So the thing about this problem is to realize that everything's independent here. The only things that really matter in terms of this problem are what times the marker touched every single cell. So I could mark all the times. So this would be time 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way around. But then when you come back around here, this cell right here was hit at time 7 and time 19. So for it to be clear, I need to know if it was drawn over and it's clear, then I need to know the latest time that that was written over, because I had to have had my marker dry out at that time or before that time. And if it's marked, what I need to know is the earliest time I ended up hitting that cell, because basically I need to ensure that the marker dried out after that. I think it's actually latest in both cases. Yeah, I need to know the latest time I ran over the cell in both cases. Oh, and the earliest time, because if this was time 7, potentially I could write over this cell in that regard. Yeah. So if the first time I hit this was time 7, I could have potentially erased this position at time 7. And so for every single cell, I need to know the earliest and latest time the marker possibly hit. The problem is these commands could go up to 100,000 in length, and there's 10 to the 5th commands. So there's 10 to the 5th commands, the length, oh no, there's 1,000,000 commands. So 10 to the 6th commands, and each of these commands could go out to 10 to the 6th. You could have this weird rectangular grid. So there's just a large number of commands that could happen. So I need to do this really quickly. So the idea for this problem is to realize that the pen going around, there are only 1,000,000 pen commands. So what we're going to do is we're going to break these up into operations that could have occurred on the page. So the type of operations, or I could go right, I could have gone left, I could have gone up, or I could have gone down. And we're going to handle each of these operations independently. So what I'm going to do is I'm going to trace through my commands and then break them into lines going right, left, up, and down. And then what I need to do quickly is mark the page of when these commands hit the page last and earliest. So for each direction, I'm going to handle it independently. I'll look at a single row and know that I had a bunch of commands. So I might have had a command that hit this part, and this part. So it might have hit this part from time 7 to time 8, 9, 10, 11, 12, 13. It might have hit this one from time 200 to time 201, 202, 203, 204. Then it might have hit this one from time 1000 to time 1004. What you'll notice is none of these interval times will overlap for going over a position. So conceptually, I'm drawing them at different locations, but they're really all on top of each other. So I'll draw that real quick here. So it's this, this, and this. So I'm actually drawing them all over one location, but I'm breaking it up for clarity. And so what I'd like to know is I'd like to know what time, the earliest times things occurred. Well, obviously for this interval, this would be 7, 8, 9. Oh, wait. Yeah, 7, 8, 9, 10, 11, 12, 13. And then these would take over. So it ended up being 202, 203, 204. And if I want the latest times, it would be 7, 8, 1000, 1001, 1002. And then I break into my 200s. All right, so I need to pre-compute both these values in terms of a sweep. So what you'll notice is these lines all go upward, and they have a start and end time. So what I'm going to do is I'm going to run a sweep from left to right. And now I'm going to maintain a solution bag that keeps track of things. And then I'll decide what data structure I need based off the solution bag. So I'll sweep from left to right, and I'll keep track of what intervals are active. Well, the easiest way to keep track of that is when did the start of the interval occur? So I'll characterize it that way. So I'll have something like 7 or 1,000 or 200. That's how I'll characterize each of these intervals. So if I hit the start point of the interval, I can keep events, an event queue. So if I hit the start point of the interval, I'll know to add 7. If I hit the end point of the interval, I need to delete 7. So I need to add and delete numbers in my sweep. What's the second thing I need to do? I need to know what the minimum value is in my data structure. So in this case, what's that 7? And when I pull it out, I'll know how far along I currently am. So I can take the distance from where it started to where I currently am and figure out what the number is I'm supposed to paste into that value. So I need to be able to identify min value. And then I also need to identify max value. So my max value is 1,000. And that would be useful for this piece of the query. So I could identify what the max value is at a given time. So I know that these intervals are completely disjoint. So this is going to be a unique identifier, just having that first value in the beginning. So just from this analysis, I need something that can add and delete numbers, unique numbers, identify what the min value is, and identify what the max value is. In Java, the easiest way to do that is just a tree set, because you can have first and last in the tree set. And you can also have insert a value, delete a value. And it's exactly what we need. And so this seems like a really simple solution. What you do is you identify each of these left-right arrows for every single row and column. And then for each row and column, you run this sweep, up, down, left, or right. And you update each of those cells. And then over all possible sweeps for every single cell, you maintain what the min and the max are for each position. So you'll get a grid, a 2D grid of all the possible cells. And you'll have the first time it ends up hitting that cell and the last time it ends up leaving that cell. And you'll end up being able to compute when's the earliest time the marker could get there, what's the latest time the marker could get there, or is it even possible? So it's funny because a lot of people, what they did is they realized, oh, there are these increasing sequences. I need to mark intervals of times where this ends up being the best possible, and then they do a range minimum query over the entire data structure. So immediately by just looking at this problem, they started thinking segment trees. So you would need a segment tree that could query a range and then tell you what the min is of that range and tell you where it occurred, and then you mark that cell in the segment tree and compute this 2D matrix that way. But just by doing some analysis with the solution bag, you can get rid of the segment tree entirely and just use a tree set. So this is really the advantage of solution bags, is just as a different way of thinking. You can look at what you need in terms of analyzing the problem and then find your data structure from there and not follow your first instincts on what the data structure should be. So that's the data structure so far. So the one comment was, I thought we only needed last. Oh, in terms of the whiteboard problem, I think you need both of them, but you might only need last. I can't remember, honestly. It's been a while since I saw this. If you're interested in seeing my implementation of the solution, I can give you all a link. 1 second. Yeah, so do I need just the max or the last? So I wanted to check up on that first. Oh yeah, you only need the last time the coordinate got touched. So you don't even need to identify the min value because the last value is all that's needed. Right, and then you need the earliest time it was last touched and the latest time it was last touched over all possible colors. Yeah, so you only need to identify what's the latest time something was touched. So I just identify this max value. So that was an error, but that was corrected. If you want to see my solution to how this was coded, you can go look at SER judging. It's at vanb.org. And if you scroll down on that page, you can look at whiteboard _font.java. And you can see how I implemented it. It's basically just the sweep idea with tree sets. And I tried to reuse as much code as possible in terms of finding the answer. Right, and so tomorrow, if any of you are interested, North America is having a practice on caddis. So I posted about this in the blog, but for those of you who are preparing for World Finals or interested in preparing for World Finals, you can go see that practice. UCF is going to be competing tomorrow. It should be a lot of fun. And I'll be UCF Death Valley. So if anyone didn't know, this year our naming scheme was national parks in the US. And so that's why we have teams like Badlands or Joshua Tree or Pinnacle or Zion or various things like that. And so I'm going to be competing as UCF Death Valley. So I subvert the naming scheme ever so slightly to be a judge, but then to be not a judge, coach. But then still fit the naming scheme here. And so it should be a lot of fun. Yeah. And then next week, so which one is UCF's World Finals team was a question that was asked. That will be UCF Badlands. So if you compete tomorrow and you want to compete against another World Finals team, Badlands is the World Finals team. Yep. And so next week on Algorithms Live, what we'll be covering is talking a little bit more about solution bags. I'm going to go over an algorithm called pitcher pouring. And you're going to see another technique for using solution bags. And then the week after that, I'm going to cover convex hull optimization. Which is also something I consider solution bags. So if you put both these two techniques together, you'll get really comfortable with solution bags as just a different way of thinking and realize that all these data structure like DP problems where you have to speed it up with a data structure, you can all start viewing them all as really just the same kind of technique, whether it's convex hull optimization, whether it's replacing it with segment trees, whether it's replacing with Fenwick trees, whether it's stack invariance, doing things with double-ended queues. They'll just all mesh together, and your analysis of these data structures will lead you to the technique as opposed to guessing what the technique will be. In my opinion, it's a good way of thinking about problems. And you'll see some more examples of more complicated invariants. So we saw some simple ones today that we could just identify in the problem, something that needed to be put on the data structure to speed things up. And once we get past convex hull optimization, I actually have some really tough problems that we could solve using this technique that require even more analysis. So I'll try to lead into those in the future weeks after we get through convex hull optimization. So it should be a few good coming week. Yeah, convex hull requested and given. Yeah, so that's the coming weeks. So I'll see you guys all next week, and it should be a good episode. And I hope to see some of you on the scoreboard for this North American practice. It's open to anyone, so you can just register. So go look at the live blog, Algorithms live blog. Keep calling it a live blog. It's not really a live blog. Just go look at the link there. You can sign up through Caddis. It's on Open Caddis, and yeah, it should be fun to compete.